Hi, recording is rolling. Welcome to Thursday, August 31st. Oh, I hope you guys made good use of Hurricane Day. We were not in school yesterday for Hurricane, just for video context here. I was able to write your quiz and do some stuff. I hope you guys were able to do some stuff, maybe get a good break there. All right, so I got a start question for you guys. Then we're going to do a conceptual question. So it's a little bit out of order there. Okay. The conceptual questions, by the way, are on the back side of the page with the boxes on it. Okay. In this page, I'm going to pick up from you guys Tuesday the 5th, which is coming back from Labor Day weekend. Okay. So also across the day, I got a couple sets of graphs for you guys, and I'll solve some of those with you. Okay. All right. So first question here, and as I hit this starter question, there's a few Kahoot questions that are pretty similar to starter question, or same scenario. So say you take a ball, throw it straight upward at 30 meters per second. The only question I'm asking right there is what is the maximum height, but we're going to do some other stuff with it too. But can anybody figure that out? Take a ball, throw it straight up at 30 meters per second. You're right. You do need. How many variables do you have to identify before you can solve any of these? Three. You do need three things. I only gave you one number. Is that solvable? Wait a minute. Seems intuitively. I mean, guys, if you're on Earth and you throw a ball straight up at 30 meters per second, it will max out at some height, right? That should be determinable, right? Huh. Hey, maybe there's some stuff that's implied that they didn't actually point out here. What could possibly be implied? Gravity field. So now we have two things, right? Okay. Let me make a little checklist here. Oh, whoops, I don't know how to do that here. Take a ball, throw it upwards. Okay, so if I make my checklist, tax VV checklist, right? Remember the mass of the ball does not affect its kinematic motion. You could have a bowling ball next to a baseball, next to a tennis ball. If you throw a ball upwards at V naught equals 30 meters per second, they'll be side by side with each other, right? So I know I threw it at 30 meters per second. And you guys said what number goes here? Huh? You even got the negative. All right. I was gonna make that a whole thing, but yeah, Adam got it already. Right. How do you know that I have to throw in a negative this time? Because he's thrown it upwards, gravity pulls down. Exactly. There's a difference in direction, right? So the fact that you throw it upwards and gravity's pulling downwards, right? So like if these were the same sign, it might be like I was at the top of the cliff and I chucked it straight down, or maybe I threw it up and gravity's repulsive, so it's like blowing it straight upwards like a rocket. And then all my answers are going to make no sense, right? Yeah. Now, could you call gravity positive and the throwing direction negative? Would that also be okay? That'd be okay too, as long as these guys have opposite signs, right? But if you're trying to solve for maximum height, that only looks like two things. You guys said we need three kinematic variables. There is one more thing you can figure out to get H max. What's one more thing that we actually do have? Yeah, okay, so we're trying to solve for a displacement. Calls H max. That's what we're trying to solve. Okay. There's one more thing we actually do know. The velocity final. Velocity final. What's final velocity right here? 0 meters per second. Okay? Because whenever you see a maximum height question, man, you guys figure that way too fast. I don't know what's going on this year. I don't know why all these students are figuring out everything so fast. Okay. Got a sharp class. Yeah. Final velocity would be 0 meters per second if we're going from point A to point B. You guys see initial to final? Right? Is that whenever you're asked a maximum height question, that's something you can consider, right? Oh, sorry, that's a little sloppy handwriting. V final. Okay. All right, so now let's break out the three amigos. We're trying to solve for maximum height. That's like a displacement question. We know the acceleration and the starting and final velocity. And notice I did not explicitly give you time, and I'm not asking for time. So now there's more than one way you can solve this. But which one of these three expressions will lead directly to the answer? The third one. Here, because if you pick the first one, the problem is so you can solve for displacement, except that you don't quite have the time right away. So it's like, well, maybe I could get the time from this and I could substitute it up to here, which that would be okay, but that would be like a couple of steps. Okay. Yeah, this third one will directly get you the answer. So yeah, there's more than one way. Both get you there. Bf squared equals v naught squared plus 2ax. Okay. Now this goes to 0. Yeah, point A to point B. Square is still 0. We're throwing at 30 meters per second. Square that. Plus 2 times negative 10 meters per second squared, h max. And we're solving for h max. Right? All good? Pretty good? Right. So, now we just got to do some algebra. Guess what's 30 squared? 900? Subtract that number. Negative 900 meters squared per second squared equals negative 20 meters per second squared times h max. What's 90 over 2? 5. 45. And the unit would be meters. 45 meters. Hey, you know what? Let's just sort of another way. Let's say how much time. Guys, if you throw it at 30 meters per second, it goes to 0 by the time it gets to the top. It's accelerating 10 meters per second. Right, downward, I guess, right? How much time is that to get to the top? What's 30 divided by 10? 3? Does that mean 3 seconds? Right. Let's go back to my picture. It looks like I took a picture every second. Tick, 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 tick. You guys see that? You guys see 3 seconds up? Right. If it's 3 seconds up, so you throw it straight upwards to 30 meters per second. How fast is it moving after 1 second? So it loses 10 meters per second because it's slowing down, which means now it's down to what? 20 meters per second. How fast is it moving right here? 10 meters per second. How fast right here? 0 meters per second, but we already said that, so we can solve this. Right? Then it's going to fall down 10, 20, 30 meters per second. Right? All right. Okay. So you could do that. You could take the time to 3 seconds. You could plug it in here. And you could solve it that way. You still get 45 meters. Okay. How about this? A little bit different perspective. Suppose you were on top of this cliff and you drop the ball. How far does anything fall in 3 seconds? Here, you guys saying 45 meters? 45 meters? In 3 seconds, it's going to fall 45 meters? Is that x is 1/2 gt squared? Right, you guys remember that? Right? Hey, that's the college equation, isn't it? X is 1/2 gt squared, as long as it starts from rest. Right? If you drop a ball off a cliff, it starts from 0 meters per second. Okay. Let's do one more perspective, and then we'll switch over to Kahoot. Let's do a graphical perspective of this. Okay, so same scenario. Let's just turn this into I'm just going to do a v versus t graph. This is v versus t. Velocity in meters per second as a function of time in seconds. Okay. Let's call up positive and down negative. So up is positive, down is negative. That's the way we just solved it anyway, right? Okay. So I threw it up at 30 meters per second. Right? Then it starts slowing down. Guys, what's the rest of that graph going to look like? Can you guys imagine what it's going to look like? What do you guys think? At time 0, I left my hand at 30 meters per second upward. After 1 second, how fast is it going? So it loses 10, so now it's down to 20 meters per second. After another second, it's down to 10 meters per second. After another second, it's down to 0 meters per second. Hey, is that a linear relationship? Okay. Guys, what's going on physically at that point? Bam, right there. What's physically going on? It has 0 velocity, which means it's where? At the top. This is h max, isn't it? This right here is at h max. Okay. Guys, what's the slope of that line equal to? Negative. It's negative. It's going down, right? Negative what? Negative 10 meters per second squared. Because we're on Earth, right? It's losing 10 meters per second every second. How about this? What property of v versus t tells you something about displacement? It's not the coordinate, it's not the slope, it's the what? Like the accumulated area under the curve? What is the area of that there triangle? 1/2 base height?
Yep. So base is 3 feet, height is 30.
Uh-huh.
So 1/2, 3 is 30 is
45 meters. Right? There's the graphical answer to the same question. Right? Ooh, guys, why did I draw all this over here? What's going on over here? What's this mean? Ah, it's falling back down. In fact, if it's 3 seconds up, do you think it's another tick, 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 3 seconds back down? Okay. And it's crash landing in your hand. How fast is it crash landing in your hand? How about negative 30 meters per second, right? 30 meters per second in the direction of gravity. Ah, you guys can figure that out? Good. You guys ready for Kahoot? Kahoot. All right, let's switch over here. Oh, look at you guys go. Oh man, my classes are on this year. Ready to learn. Ready to learn.
I can't see that.
No, what? Oh, why not? One possible unit of speed. Yeah, there you go. So miles per hour, kilometers per hour, light years per century. This all kind of distance per time. In this class, of course, our go-to unit is meters per second. All right, you guys got that one. oh, look, we got points on the board. Oh yeah. Object moves 5 meters in the first second, 5 meters in the next second, 5 meters in the third second. What is the acceleration? Acceleration. Oh, look at you guys go. 0, because there's no change in velocity, right? Let me ask you guys a different question. What's the velocity of that object? The velocity is, 5 meters per second is the velocity. But it's a constant 5 meters per second, which means no acceleration. It's not speeding up or slowing down. All right, we got Matt, Blakey, Patrick, Tucker, and Blake.
So I'm catching up. I just one question in my
Hey, where's my next question? Object falls freely in a vacuum. What actually increases? Ooh, 3 winners. Yeah, velocity. So suppose you release it at rest, maybe it falls 0 meters per second, 10, 20, 30 meters per second. Right? Now, guys, velocity picks up at a constant rate. But what is the physics term for rate of velocity? Rate of velocity is acceleration. And that's not increasing. That's doing what? Constant, right? Isn't here. Hey, you guys remember, do you guys see the poster with the table? You guys remember under the acceleration column, it's just 10 meters per second squared all the way down? That's constant acceleration. It's constant acceleration. The velocity is increasing. All right, we got Blakey, Patrick, Adam, Tucker's on fire. Blake leading the pack. Object ball's thrown straight upward and it's caught when it comes back down. The speed when it's caught. Yeah, there you go. It's the same speed as when it was thrown upward. And we sort of we're looking at it already. That's what this was, right? You guys remember if you throw the ball upwards at 30 meters per second, it goes 20, 10, 0, 10, 20, 30. Ah, so you catch it at the same speed that you threw it. No, in terms of velocity, it's just the opposite direction. It's the same speed, right? Same magnitude of velocity, same speed. Right? You guys remember that, right? All right, back over here. All right, more points. Ball thrown upward, falls back to the floor. During this time, the acceleration is always. There you go, directed downward. Gravity always pulls down. Wait a minute. What about when the ball's just left your hand is traveling upward? Guys, when the ball is being thrown upward and it's moving upward, is it still accelerating downward? Yep, gravity always pulls down. Guys, if it's moving up and gravity's pulling down, does that mean it's speeding up or slowing down?
Slowing down.
Slowing down, right? And then it hits the max height and then it starts to fall down. And then when it's moving down and also accelerating down, then it's speeding up on the way down. Right. Ooh, Aaron, Blakey, Tucker, Adam, Blake on fire. Suppose you go 300 kilometers in 5 hours. What's your average speed? Oh, look at you guys, 60 kilometers an hour. All right, another question for you guys. All these kinematic equations, like those three amigos up there, those kinematic equations, do those involve average or instantaneous velocity values? What are these? Average or instantaneous? Like instantaneous, right? Right. In this class, I'll very rarely ever ask you an average velocity question. We usually care about instantaneous, like what's going on at one particular instant. All right, Patrick, hop into the top 5. Blake still on fire. Made a fire extinguisher. Ball is thrown straight upward. Top of its path, its instantaneous speed is. Instantaneous speed. 0 meters per second. Okay. That's a good way to figure out the question, like, what is the maximum height of something, right? Well, see, I know at the very top it'd be moving 0 meters per second because it's like turning around. Okay. All right. Same scenario. At the top of its path, its acceleration is. Acceleration. Yeah, there you go. 10 meters per second squared. Guys, if you throw a ball straight upward, as soon as it leaves your hand, is it under the influence of gravity?
Yeah.
Yep, it's in free fall. Then it reaches the maximum height, and then it comes back down. From the point that you release it to the point that you catch it, all in between, is it always accelerating down in 10 meters per second squared? Yep, sure is. The acceleration free fall. There. Ooh, Adam has caught the fire. It's moved to the top spot. Car accelerates at 3 meters per second squared. How much time to reach 15 meters per second? Starts from rest. Everybody winning. Is 3 times 5 is 15? Okay. So, which kinematic equation? Is that VF equals V naught plus AT? Or just, if you like, V equals AT?
Why is it 3 minutes squared?
Okay, because the speedometer needle is moving, right? Right. In fact, if you like absolutely gunned the gas pedal, it'll go like and be really fast. But if you just kind of tap it a little bit, maybe it moves up a little bit slow, like right. So the numbers that your speedometer needle points at are in the can be in units like miles per hour or meters per second. So when that needle is moving, it's moving at some rate. It's like changing some meters per second per passing second, right? Right. So that's why we're like 3 meters per second squared tells you that the car picks up 3 meters per second during the first second, and 300 meters per second during the second second. It's like meters per second per passing second. That's what it is. Yeah. Okay. All right. Yeah. It's a good question though, because that's one of things in physics. Right? All right, Adam, hold on to the lead. So on fire. Freely falling object starts from rest. After falling for 5 seconds, its speed is after 5 seconds. Oh, look at you guys go! All right, 50 meters per second. So that's also B equals GT, you could say. B equals AT, right? So 10 meters per second squared times 5 seconds brings you up to 50 meters per second. Right? Oh, I remember what I was going to ask you guys. During that same 5-second fall interval, how far does it fall? About 125 meters. Wait, how would you know that? College, right? That's your 1/2 AT squared is the fall distance. Then you guys got what was the speed? All right, Zane's on fire, hopping in the top 5. Adam's still got the lead. Look at the speedometer of a moving car. You see that car is what? Yeah, instantaneous speed. Yeah, so your speedometer tells you how fast you're going at that instant, which is also the numbers that feed into these equations, right? Like instantaneous values. All right, Chloe hopping on top 5. Adam still got the lead. Car starts from rest. After 5 seconds, picks up to 30 meters per second. What's the acceleration? Oh, there you go. 6 meters per second squared, right? So we got a change in 30 meters per second. Happens in 5 seconds. Divide those two. Looks like the speedometer needle is moving 6 meters per second per passing second. Oh, yeah. All right, Patrick hopping in the top 5. Adam still got the lead. In a vacuum, objects fall at constant what? Yep, constant acceleration, right? Constant acceleration, right? So the speed's always changing, but the rate change of that velocity is constant. Constant 10 meters per second squared, you could call it. I got Patrick, Tucker, Blake, and Adam on fire. As drops of water fall from a leaky faucet. No. Ooh, okay. That looks a little bit challenging right there. Get further apart. Here. So do you guys remember? Here we did the table version of this, and we did the 3 graphs version of this. These two are the same scenario, though, right? You guys see dropping off a cliff, right? So, here's my ball dropping off a cliff, and it's really here as a function of time ticking. How far did it fall? 5 meters, then it's up to 20 meters, then 45 meters, then 80 meters, then about 125 meters, right? So do you guys see how it's like spreading out, getting further distance it falls every successive second compared to the previous one? You guys see that? Right. Because it's always going faster, right? It's going faster and faster. So every second it's going to go further. Right? Now, if you replace the rock off the cliff with, what if I have a leaky faucet right here? It's going drip, 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 drip. You watch the drips of water. It would also kind of look like that, wouldn't it? You guys think? Huh. I think it would. You figured that out. Which 2 of you? Patrick and someone. All right. Bob can jump off the ground with twice the jumping speed of Alan after his feet have left the floor. Yeah, they have the same downward acceleration. Guys, if you're not grounded on the floor, if you're like flying through the air, jumping up, jumping down, jumping to the side, if you're in free fall, if you're heavy, if you're light, doesn't matter. Everybody has the same downward acceleration of 10 meters per second squared. No matter how fast, doesn't matter which direction. If you're in free fall, all right. What is the value of G at Earth's surface? On 100%. Come on. Ooh, so close. Yeah, about 10 meters per second squared. There you go. About 10 meters per second per second.
There is no gravity.
Balls drop from top of a cliff. Every second its speed increases by about. Yeah, 10 meters per second, right? It's changing its speed 10 meters per second every passing second. Actually, those last two questions were like almost the same question, weren't they? Right? All right, we got Patrick on fire, Tucker, Blake, Adam. Drop a feather and a coin in a vacuum chamber. Which one hits the ground first? Vacuum, in a vacuum.
Yeah. I didn't see that.
It's a tie. It's a tie. There you go. All right, Josh out there in the top 5. Adam's still in the lead.
Yeah.
Projectile fired straight upward at 30 meters per second. I think we just solved this. What's the total time to return back to the ground?
Oh, you were meant to get a paper.
Yeah, so if you pick 3 seconds, you're probably taking 3 seconds to get to the top, but you still need 3 seconds to fall back down. That's why the total time 6 seconds. Right? Here, let me flip over here and remind you guys what we were doing. Okay. So, you guys, the starter question was this, right? You throw a ball straight up at 30 meters per second. Right? Well, actually, I asked you maximum height, but we analyzed this a bunch of other ways too, right? So it takes 1, 2, 3 seconds up, 1, 2, 3 seconds down, right? Here's the graphical version of the same thing, right? 1, 2, 3 seconds to the peak, 1, 2, 3 seconds to back down. If you like, you could use this one, you could use this one. You get the same thing. Let me show you guys. Suppose you just use this one. Guys, if you throw a ball straight up and you catch it at the exact same location that you threw it, what is the displacement from beginning to end? 0. Let's put a 0 right there. Equals, I threw it up at 30 meters per second. Some time to get back, 1/2 -10 meters per second squared times squared. And the question is how much time? Are you guys yet? Now, at a glance, this might look quadratic, except that because this is 0, can we just factor a t out? What's half of -10?
-5.
-5. Subtract 30 over. Divide by those -5 seconds. So what's the time? 6 seconds. Okay. Alternatively, you could use the second one. Because if you throw it up at 30 meters per second, how fast is it, bam, crash land back in your hand? -30 meters per second. What's -30 minus 30?
60.
-60?
-60 equals -10p, so that just t equals 6.
It's still 6 seconds. There you go. So a little bit of overkill, but there's a bunch of different ways to solve it. You always get the same answer. Patrick hopping back in top 5. Sophia has a streak of 5. Adam's still in the lead. Oh, last question. A jumper claims a hang time of 6 seconds, which is kind of ridiculous. You're on the ground for like, okay, if that's true, you could jump a height of what? Right. So some little kid says, I can jump in the air and I'm in the air for 6 seconds. Like, yeah, right, kid. Because if that were true, you're also telling me you could jump a maximum height of what?
Oh, yes. Also, like, none of those are answers like that, right? I was doing math.
Ooh, two winners, two winners. Here, let's go here. Okay. How many guys caught on that this is the exact same scenarios we've been solving all day today? Right? Because guys, if you throw something up at 30 meters per second, how much time is it in the air for?
6 seconds.
6 seconds. So that's the same thing. We got some little kids saying, hey, I can jump in the air for 6 seconds. Wouldn't he be jumping up this fast? And how high could he jump? 45 meters. H-max is 45 meters. We already did this. And here's the graphical version of the same thing. We already did this. It's the area of that triangle on a V versus T. 45 meters. Right? Got a couple of winners. Hey, where's my mouse cursor? There we go. To the podium with the bronze plate, with the silver. Adam. Ooh, who got the gold? Who got the gold? Yee! Ooh, right in there. Good for the win. And Tucker Patrick round out the top 5. All right, nice job, guys. Nice job. All right, I got some posters for you guys. Got some posters. Okay. Right. Oh, hey, look what I have set up here. X versus T. Guys, got your notes out? Got your notes out? All right, I'm going to take a trip around the room. I'm going to see who can get these graphs correct. X versus T, V versus T, A versus T. For this scenario, a car brakes to a stop. Car brakes to a stop. What do those graphs look like? Quick trip around the room here. You got to get these. Who knows what's going on? Who's gonna get those 3 graphs? Give guys a couple of hints. One is guys, if the car's braking to a stop, is it starting from rest? No, that wouldn't make any sense, right? It must be starting with some speed. So I think on the V versus T, I'm gonna have some initial velocity. It's got come to a stop. Right. Also, I should have thrown in another word here. I should have thrown in the word uniformly. The car brakes uniformly to a stop. And all that means is that it slows down at a constant rate. Okay, so that's like a usual assumption in our class anyway. My car brakes to a stop. Who's gonna figure out what these graphs look like? Who's gonna get them? Gotta get at least one winner.
Oh, wait.
All right, Patrick just figured out the V versus T. Yeah, Adam figured out the V versus T. All right, let me take one more trip around. See if I can get some more winners here. Ooh, close, close. All right, Tucker got the V versus T. Zane got the V versus T. Oh, Candace figured out the X versus T. That's the first winner on X versus T. Yeah, okay, so V versus T. Aaron's got the V versus T. Oh, yeah. So Ethan got the A versus T. Oh, Alexandria's got them all. All right. Alexandria's the winner. Oh, yeah. So looking for that right there. Okay. All right, so car starts at some initial speed, then hits brake. Velocity goes to 0. Now, I should have thrown in the word uniformly, which would just tell you the slope is constant. And guys, the slope of this V versus T always represents what physical property? Acceleration. And guys, the fact that it's a negative slope tells you that acceleration is a negative value. In fact, it's constant slope, constant acceleration, right? Is that? Okay. I'll say about that. Oh, guys, if the car is moving forward and is braking, that's another indication that it's moving forward, it's accumulating positive displacement, but its acceleration would be negative. right? See, like if acceleration was positive, that'd be like if he was slamming on the gas pedal and go speeding up. No, that's not what's going on. Right? Now the kind of tricky one that a couple of guys got was x versus t. X versus t. Because look, like here, suppose I break down the v versus t into different intervals. You guys know the area under the curve represents how far, right? During the first second, ooh, it looks like it went pretty dang far. So it accumulated a lot of displacement. During the next second, kind of medium, like Goldilocks, right? Didn't go as far. And that last second, you got a little itty bitty triangle right there, which says like as it's slowing to the final stop, it's still moving forward, but not very much. Oh, guys, what shape is this? Starts with the P. Parabola. And is the vertex right here? Is this the vertex? That's the vertex right there. Huh. Right where it stops. That's the vertex. Right, you guys good there? Got one more linear motion poster for you guys. Let's get a broad view of velocity versus acceleration. Velocity can be positive or negative. Acceleration can be positive or negative. What does that mean in any of these four contexts? Also, either this could be zero. I didn't actually include that on this table. Okay. So, guys, what does it mean for velocity? Actually, let me back up. Different question. Okay. Which one of these, velocity or acceleration, which one tells you the direction of your motion? How many guys think velocity tells you the direction of your motion? Velocity? All right, there's my winners right there. Yeah. Okay, so if I say moving forward, did you say, oh, velocity is positive? If I say moving backward or right, it could be negative, right? Or if you're dropping something off a cliff, whichever way you define as positive or negative, up or down, right? Your direction of your motion is told by your velocity, right? Now, if you take that in conjunction with acceleration, what does it mean for the velocity and the acceleration to have the same sign? What does that mean the object is doing? Speeding up or slowing down?
Speeding up.
Speeding up. Okay. Here's what the graphs look like. In fact, these graphs sure do look a lot like dropping a rock off a cliff, right? If you define down as the positive direction, that's a bam, that's a match in your notes. You guys see that? Moving forward, speeding up, or in the positive direction, speeding up. Okay. Hey, what would it mean for velocity to be positive, but acceleration to be negative? What does that mean? Yeah, and also moving which way? Moving forward, slowing down. We just did that. That was the car bringing to a stop. We just did that. That's these guys right here. It's the same thing. You guys do you see that? Right? You guys good? Oh, all right. Now, probably the trickiest quadrant on this whole table. What does it mean to have negative velocity? Well, let's just start with that. Negative velocity, which way are you moving? Forwards or backwards?
Backwards.
Backwards. Okay. Let's say at the same time you have positive acceleration. What would that mean to have a mismatch in the signs? So you got your car in reverse. You're going backwards. It's backwards slowing down. You guys say backwards slowing down? You guys are right. Man, I got a sharp class. Backwards slow down. Anytime there's a mismatch in signs, look, these two quadrants right here are, you got positive, negative, negative, positive, right? If there's a mismatch in signs between B and A, that means you have a slowing down situation. Okay. Finally, what would it mean to have your car in reverse and also have negative acceleration at the same time? That means you're doing what? Speeding up in the negative direction. So now not only is your car in reverse, but you're hitting the gas pedal at the same time in reverse. Right? You're accelerating in the same direction. You're also moving. Right? Okay. That's here. That's this poster right here. You want to see that a little bit more? And I did change the colors a little bit. The colors on this are a little bit different, but same idea. All right, guys got that? All right. Finally, I did want to allocate some class time where you could solve some of these puzzles. Since we only got about 6 minutes of class left, I'll just go ahead and pick some and solve them with you guys. Okay? All right. Oh, guys, when is this paper due? Tuesday the 5th. Tuesday the 5th. Where did I write that? Here it is. Tuesday the 5th. Right? You guys got that? Cool. Guys know we got Labor Day weekend coming up, right? All right. So back on Tuesday, I think I did number 5, number 6 with you guys. Let's skip over to number 15, 16. Number 15, 16. A ball is thrown straight down with given initial velocity from the top of a cliff on Mars. Ooh, Mars. About to have some spooky gravity going on. Oh. Suppose you know the throwing speed and the crash speed. How much time and what's the height of the cliff? So here's the height of the cliff. Here's the ball. We're going to check this straight down with some initial velocity. It's going to be a crash landing at some faster final velocity. Right? And the gravity field on Mars, well, we know what the gravity field on Mars is because they gave it to you. Right? Let's set up a checklist here. Right, so here's our kinematic variables checklist. Right? You know it's gravity on Mars, so we're using 3.7 about meters per second squared. You know the throw speed. Now, my numbers are probably different than your numbers. There's a bit different versions of this. My paper says 9 meters per second. And somebody brought a radar gun to this party and says, right when it's crashing, it's going 26 meters per second. 2 questions. How much time did it take to reach the bottom? And what's the height of the cliff? Right? Right, you guys go there? Let's solve for time first. Solve for time. Which of these 3 amigos will solve for time? Which one? First, second, or third? Second, definitely the second. So here's why you would not want to pick the other ones at this point. If you pick the first one, there's 2 unknowns. Like, okay, you don't know time, so maybe I could solve for that. Except you also don't know the height of the cliff yet either. So 1 equation, 2 unknowns, that's not quite solvable. The last one, actually, you could have used the last one to solve for the cliff height. You could do that. Right, but here, if we're solving for time, we got to use this one, right? All right, let's do that. Let's go. Final velocity equals initial velocity plus, you can say AT, you can say GT. Right. We're going up to 26 meters per second from 9 meters per second. And we're picking up at 3.7 meters per second per passing second for some amount of time. Right? Oh, now it's an algebra problem. Right? Subtract, divide. Right? So time is going to be 26 meters per second minus 9 meters per second, all divided by 3.7 meters per second squared. Okay. So 26 minus 9. So I'm looking at about 4.6 seconds is the time. All right. Great. Now, every one of these scenarios on this page is unique in some way. Right? And there's a couple of questions I can ask you on each one, including this one. The other question is, what's the height of the cliff? Okay. So there's 2 ways. Now there's a couple of opportunities. Could we use either this equation or this equation? Yeah, right. Because now you know the time. Yeah, pop it in. Right. I'm going to take this third one because that's a direct way to get it based on the information I gave you. So I'll go and do that. I'm going to say BF squared equals V naught squared plus 2AX. How about that? I want the height of the cliff. It's going to this many meters per second from this many meters per second. Don't forget to square those if you're using the same method I'm using. 3.7. And for x, I'll call it h like the height of the cliff, because that's a way to represent displacement. Okay. So 26 squared minus 9 squared. All right. Well, 26 squared minus 9 squared. These have units. All divided by 2 times 3.7 meters per second squared. Okay. Right, there's kind of a general way to get h. Okay, in fact, if you like, do you guys see what just happened? So I did final velocity squared minus initial velocity squared, all divided by 2g. You guys see that's like the same thing? Right. This right here is a general way you can get the answer. So now you can like hop planets, you can change your throwing speeds, right? You guys see that? Let's see what we got here. That divided by 2 by 3.7. I'm looking at a height of 80 meters, about 80 meters I'm getting. Okay. All right, you guys good? All right. Yeah, bell rings about a minute, so I'm gonna have to stop right there. But got more adventures lined up tomorrow. Hey, you guys have a great rest of your day.